Welcome. On this beautiful 1st of August, Swiss National Day, I want to say something about the discrete variational problem. So we have seen that if you have a manifold, a q-dimensional manifold, and we have a function to set with k plus 1 elements, then we can talk about submanifolds. And we can compute the expectation of quantities of these submanifolds. They are completely determined by the combinatorial data of the host manifold. So that was the random manifold theorem. But we can also look at the maxima and minima, and like in the continuum, you can, for example, take a 3 manifold with boundary, like a ball, and you can fix some points on the boundary, and you can look at the connections, you can look at the Euler characteristic or length or volume of the manifolds which occur here with this boundary constraint. So that's one of the problems we can look at. We can look at the problem to fix the g, the function g on the boundary, which means fixing a manifold on the boundary, like here, and then we can look at all the submanifolds which have this boundary, and then there are natural variational problems. One example is the area, for example, or volume. Another example is the Euler characteristic. And I'm mostly interested in the Euler characteristic because it's a nice topological quantity. And so here are kind of some 4 cases which can occur. Just fundamentally, you can have either that q is even and k is odd, like here we have a 2 manifold with boundary, a disk, and we have k odd. In this case, k is equal to 1, and then what we have is we fix points on the boundary, and then we want to kind of find submanifolds. So in this case, that's not interesting because they are linked. The Euler characteristic of the boundary is twice the Euler characteristic of the interior manifold. That's true in any of these situations where k is even and k is odd and q is even. Another case we can look at if q is odd and k is even, so then everything reduces to the variational problem for a manifold without boundary. Because, I mean, in this case, when you fix the boundary, then there is no choice for the Euler characteristic of the interior. Again, we have this relation here. Interesting is when q is even and k is even. I like this case because the smallest case where this is really interesting is when q is 4 and k is 2. And that's motivated by physics. So what you have is you have a kind of a universe G, and you have the boundary, which may be space, and then you have conditions, fixed conditions, circles. These are then one-dimensional manifolds, and then you want to see, what extremizes. In this case, what minimizes the Euler characteristic. So in this case, Euler characteristic is minimal. That produces interesting manifolds. And I maybe show an example in a small case. I was actually looking at this case. This is kind of very similar where q is odd and k is odd. Like if you have a 3 manifold and you have k is equal to 1, and then you get 2 manifolds inside and again you have the same situation here, but then what happens is the boundary is 2-dimensional and the interior is 3-dimensional. But that's the interesting case because then we get 2-dimensional manifolds in the interior, and we can look at the minimal Euler characteristic. And there I kind of made experiments, and what happens is, because this is a finite variational problem, there are finitely many cases, you can go through all the possible cases and you can really find the minimum. And for larger ones, there is no chance. The probability space has k plus 1 to the v elements, and that's huge. already for smaller cases. But I have made experiments with, you know, maybe a dozen points, and then you can see maybe the Euler characteristic is minimal for genus 4 manifolds, and then you can look at these cases. Another interesting case, of course, is the case when you look at the volume. That's kind of like a Plateau problem where you have the minimal surfaces. Another interesting case is the Dirichlet case where you have, which is an analog of looking at the Dirichlet problem where you want to minimize the energy. And in this case, it's essentially just f1, the number of edges where the function changes. So that's it for today.